And welcome back to the afternoon session of the graduate school, and welcome to all of you who are online. So I'm very pleased to introduce Stephen Amelotte, one of the rising stars in our field, who's going to talk to us or give us some background in the subject in which Fred was working for the last 15 years of his life. So I hope you'll feel free to ask questions at any time. And with no more to say, welcome, Stephen.
Thanks very much. I'll start with a big thank you to Fred. I had the incredible good fortune of getting to work with Fred for a couple of years at Rochester, where he taught me lots about polyhedral products and lots of other stuff, some of which I'll try to pass on in these lectures. And yeah, him and Kathy were just incredibly kind and generous to me while I was there. So very thankful that I got to know him, and I'm thankful to the organizers for putting together this month of events in his honor. And then there's some non-organizers I should thank, like I'm thinking Taras Panov and Martin, who's not here, Martin Bendersky, Lisa Jeffrey, and Don Stanley. They all organized similar events recently, like last year and before that, where they ran similar little mini grad courses like this. So I'm going to shamelessly lift bits and pieces from all of their lectures. And then some other people here I should maybe thank are like Larry, who's here, and Lewis. All these people in one way or another gave input into these lectures. So here are the main references. Polyhedral products sort of come out of toric topology, which starts in the 90s with this work of Davis and Januszkiewicz, where they introduced some broad like topological generalization of toric geometry. So some manifolds that generalize toric varieties, essentially. And then the foundations of this subject were sort of reimagined by Buchstaber and Panov using polyhedral products, which make things a little more friendly for homotopy theorists, I think. And then even more recently, this survey, Bari, Bendersky, Cohen, and Gittler in a handbook of homotopy theory. It's a great reference. So everything I say is somewhere in there. So today will, I think, just be about polyhedral products in toric topology as they arise in that subject. And so some preliminary motivation maybe for definitions. It's just why study or why care about polyhedral products? I'm just going to sort of immediately reject this question as too broad because it includes, for example, why care about products or co-products in some category. So instead, the maybe best studied polyhedral products are the ones that come in toric topology that are called moment angle complexes and moment angle manifolds. So I can definitely tell you why you might be interested in those from like a purely homotopy theoretic point of view. So one thing is these are just a very large collection of interesting spaces called ZK. We get one for every simplicial complex K, or sometimes some other sort of combinatorial input K. And by interesting, I mean they are often manifolds that admit like interesting geometric structures and have all kinds of other interesting topological behavior. And one has sort of an unusual amount of control over these spaces coming from the combinatorics of K. And this has made them sort of a good testing ground for lots of conjectures. So I'll just mention a couple right now, and maybe I should write below here. But one big one coming from toric topology, or really coming from like rational homotopy theory before that, is something called the toral rank conjecture. This is, I won't say much about it, but this is something that's wide open in general, but known for moment angle complexes. And really, I'm going to put a star here because it's possible that it's not actually known, or it's only known for like certain torus actions, but not all torus actions or something. But really, all I mean by this is that we have good bounds on the Betti numbers, set K. The toral rank conjecture says something like any space should have at least as much cohomology as the maximal torus that acts freely or almost freely on that space. And then another one coming more from homotopy theory. I'll say more about. Fred, like several people here, is a descendant of John Coleman Moore, who made the following amazing conjecture. So let X to start be, say, a finite, simply connected CW complex. And let P be any prime. Then the conjecture is that X should be elliptic, or what's called rationally elliptic. If and only if X has a finite homotopy exponent at P. Okay, so for a space to be rationally elliptic, this just means the dimension, its total, like rational homotopy groups, is finite. So in rational homotopy theory, there's this big organizing principle. It's a theorem called the rational dichotomy theorem that says all finite simply connected CW complexes are either elliptic or hyperbolic. Elliptic meaning this, and hyperbolic means that the rational homotopy groups just grow exponentially with n. So there's nothing in between. Either the rational homotopy groups of your space give up at some point, they're just zero for all n above some given n, or if that doesn't happen, they just explode and go crazy. There's nothing in between. There's no sort of polynomial behavior in the rational homotopy groups. So Moore's conjecture was that this should be related to the sort of p-local behavior. And notice I'm letting p be any prime here. So if this holds, this side should hold for any prime. So in particular, Moore is conjecturing a very deep like relationship between the p-local behavior of X just at all different primes, right? So what does this mean? This means that some fixed power of p kills all of the p torsion showing up in the homotopy groups. So p to the k annihilates like the p torsion. Pi star of X. Right, so of course for any particular homotopy group, there's such a k because these are just some finitely generated abelian groups. So we're asking for like the highest torsion order that occurs when you look out at all of the unstable homotopy groups of the space. Okay, so in general, what's the problem with proving something like this? So I've heard Steve Halperin, and maybe seen it written some places, called Selig's Lament, which is that there is still no finite simply connected space X other than a point, all of whose homotopy groups are known. Okay, I should maybe point out something here before going on, that on the right-hand side of this conjecture, by some very early results of Sayre, there's no sort of direct analogy. Like you might think the corresponding thing over here about the p-local homotopy type of X might be that its p-torsion in the homotopy groups just stops at some point and you don't see any more. But that just doesn't happen for finite simply connected CW complexes. If you're not contractible, then you sort of have infinite p-torsion. Or more specifically, if X has non-zero mod p homology, so it doesn't have to have p-torsion in its homology, just non-zero mod p homology, like a sphere, say, then p-torsion will show up infinitely often in the homotopy. So there are no there's no p-local notion of like ellipticity, for example. So instead, he's conjecturing this sort of behavior should be analogous. And amazingly, Moore conjectured this before the rational dichotomy theorem was proven. Okay, so given that we don't know all of the homotopy groups of any space X, and this is sort of asking something about all the homotopy groups of X, how could you possibly show that any X has an exponent? Fred and his co-authors give us one very powerful way, but let me start with the theorem of Paul's and then later Fred's. So method one is maybe to try to recognize your space as a retract of something which a priori has an exponent. Okay, so notice, let's see, like this assumption that X is finite and simply connected. If you dropped one of those assumptions, like if we drop the assumption that X is simply connected, then you might just think, okay, S1, we know all the homotopy groups of a circle. And there's lots of other aspherical manifolds. Or if you drop finite, then a simply connected space can just have any sequence of homology or homotopy groups that you like, right? You could consider taking products of Eilenberg-MacLane spaces or wedges of Moore spaces to just arrange to have any homology or homotopy you like. So there's certainly infinite dimensional simply connected spaces for which we know all the homotopy groups, like Eilenberg-MacLane spaces, or as Anya's reminded us, we know all the homotopy groups of like BU by Bott periodicity. So you could take some infinite dimensional space, which sort of by construction has an exponent, and try to recognize your space as a retract or something of that space. So an example is this theorem. Paul for odd primes, and then later Fred at p equals 2. So what they show is if you take the 2p plus 1 sphere, and then you look at its double loop space, and then you take the pth power map on that H space and look at its fiber. I'll denote that with this curly bracket P notation. It won't come up again later, but this just means the homotopy fiber of a pth power map. They showed that this infinite dimensional space decomposes as the double loops on a 3 connected cover of S3 across some other space. And one way to think of the fiber of the pth power map on any loop space is as a mapping space. You can check this is the same thing as just the mapping space from like 2 here. I think I want 3 here. Okay, where this M3 is like the 3-dimensional Moore space. So I want to take the cofiber of a degree P map on a sphere. Okay, so just the space whose suspension spectrum is the Moore spectrum, mod P Moore spectrum we saw in the previous talk. And also, as we were sort of reminded by Agnes, this space has a null homotopic degree P map if P is odd. Weirdly, the degree 2 map on the mod 2 Moore space is not null, but the degree 4 map is. So that makes the Pth power map on this loop space, right? You can think of multiplication by P on this space that induces multiplication by P on homotopy, but you can also just think of it as like pre-composition with a degree P map. So yeah, that's going to be null just by construction. So this is a space which I would say obviously or a priori has an exponent, and it implies that S3 does as well, which is sort of an amazing corollary here. Okay, I guess I should say like left-hand side has an exponent P at an odd prime, or P2. So P respectively 4. So this is like the first example of a space for which we know the best possible homotopy exponent. Okay, there's method 1, and then rather than trying to see your space as like a retract in some other space that has an exponent, you could take the space you're interested in X, and you could try to decompose like say X is some indecomposable space. Maybe after looping it once or more times, it'll become decomposable up to homotopy theory. So you could try to decompose like X as a product of smaller spaces. Which have exponents. Okay, so Cohen, Moore, and Neisendorfer did this for a Moore space. Got some explicit decompositions of the loop space of any odd primary Moore space anyway. Okay, I'll spell this out in a second. And using that, they actually got explicit exponents for Moore spaces, but even better, they deduce the famous Cohen-Moore-Neisendorfer exponent theorem, which generalizes that previous result to say that if P is odd, then S 2n plus 1 has exponent exactly P to the n. Right, so when n is 1 and this is the 3 sphere, it's just saying you have exponent P, and this is how it generalizes. Yeah. Actually, I couldn't quite hear. My hearing is.
I didn't quite understand how the left-hand side of having the exponent implied that S3 had exponent P. Maybe I'm missing something about loops to S3. Is that the third? Yeah, maybe I'm missing something about.
So we're saying the left-hand side can be thought of as this mapping space.
I'm okay with the left-hand side.
Oh, okay. Why does that imply the right-hand side has exponent?
No, I'm okay with that.
Why does that sorry.
S3 has exponent P.
3. Oh, the homotopy groups of the 3 connected cover of S3 are the same as the homotopy groups of S3. Notice that like, okay, yeah, S3 itself has a single free summand in pi3. Yeah. So that space could not possibly retract off of the fiber of a P power map. But once you knock it off, this we're okay.
I asked a stupid question.
It's okay. Please ask questions. My
Thank you
hearing
for
is
that.
just not
That was setting an example. Yeah. Would anybody else like to ask an equally good student question? Any other questions? Would anybody online like to ask, anyone online like to ask Stephen a question?
Maybe I should also point out related to that, that this notation here is at odds with like the stable notation for what you would call the 3 connected cover. I think stably you might put a 4 there, right? Or
Oh, thank you for getting the ball rolling. You're a good student.
okay, so you take any odd dimensional sphere, you pick your favorite odd prime, and then you look out at all its homotopy groups. You will see Z mod P to the ends showing up infinitely often, but you'll never find an element of higher P order than that. Okay, and then the third method that brings us back to moment angle complexes and how we can see this Moore conjecture holds for them is sort of similar to method 1. So something else you could try to do is like recognize your space X as the orbit space, maybe, of some space which you know has an exponent. Yeah, Paul.
Just one, you should mention Brayton Gray because you've only given the bound in one direction. The fact that there exist elements of order P to the N in loop S2N plus 1 is due to Brayton Gray.
Thank you. So Gray.
It's a gray area.
Yeah, really, Cohen, Moore, and Neisendorfer's result gives us like an upper bound on the exponent. But we know, I think basically from the image of J is what his work is doing here, is that there really do exist elements of this order, infinitely many of them. So yeah, that's why we can say exactly. Thank you. Okay, so this third method is about trying to recognize your space as the orbit space by, say, like a torus action or a finite group action, right? Some group that doesn't really have any homotopy. Then you'd have a fibration going from this group to a space that you already know has exponent, maybe, to the space you're interested in. So for moment angle complexes, first of all, Moore's conjecture turns out to be sort of easy to see. That maybe the conjecture showing again. It's easy to see that the only way ZK can be rationally elliptic is if it's a product of odd dimensional spheres, some finite product of spheres. Okay, so we know that such a space has an exponent from the results we just went over. And if you're not in that case, it's not so hard to see, basically just arguing from like the combinatorics that give rise to this space, that if X is hyperbolic, or if ZK is not elliptic, then you'll get some wedge of spheres as a retract. And a wedge of two spheres, of one of them being of dimension greater than 1 at least, is sort of a prototypical example of a space that does not have a homotopy exponent, because here the Hilton-Milner theorem kicks in and tells you that the loop space on a wedge of spheres has the homotopy type of like an infinite product of loop spaces of spheres. where the dimensions of these spheres get arbitrarily big. So in that case, zk would have no exponent. I guess I should say like no finite exponents. Okay, so the point here was just that it's sort of easy to see. I haven't given you definitions of a moment angle complex, but we'll see eventually that it's not so hard to see these two facts. And then something toric topology does. Outline the equivalence.
The equivalence at the top is just a rational equivalence, or is it actually a homotopy equivalence integrally?
Integral homotopy.
Oh, okay. Thank
Yeah.
you.
Yeah, basically you can show that the only way zk can be elliptic is if this ingredient like simplicial complex k is just the boundary of a simplex or the join of a bunch of boundaries of simplices. And the moment angle complex associated to such a thing is just a sphere. So we'll see that as like our first example in a little bit.
Any questions online? Thanks.
Okay, so that's good enough because like I said, zk, these moment angle complexes, whatever they are some huge collection of spaces. So we know Moore's conjecture holds for them, but even better, toric topology shows us that a huge class of manifolds, in particular like toric varieties and a very big generalization of those kinds of objects, can all be recognized as quotients of moment angle complexes. So I'll just say toric topology recognizes all kinds of manifolds. Finite dimensional manifolds are certainly spaces we don't know much about Moore's conjecture for. For example, toric varieties. As quotients. Let me just say this. So from the long exact sequence in homotopy sense. A free action, yes. We'll get into the details in a bit, but even if it wasn't a free action and this is a homotopy, okay. So it follows immediately from this that we get Moore's conjecture for M2. And I should say here that for some of these details, there's a nice short paper where Howe, Soon, and Theriot prove Moore's conjecture for some other polyhedral products as well, other than moment angle complexes.
Yeah, I just wanted to ask what exactly like many manifolds means.
Yeah,
Like, does
We're
this mean
gonna-
almost no manifolds or like almost all manifolds?
not almost all, not almost no either. Okay. Thank you.
But there are manifold examples.
Yeah. Yeah, so just as a reminder, this is still all under the heading of like preliminary motivation. In a second, we're going to properly start and give definitions and so forth. So you'll see exactly what kind of manifolds show up. But I'm saying, for example, toric varieties, because the typical examples are like even dimensional manifolds with a nice half-dimensional torus action. So notice a toric variety is just at least a smooth projective toric variety, say, is kind of manifold that comes with a torus action. So you could look at its orbit space a toric topology recognizes these things as themselves the quotient of another space with it. So if you were just starting from like a toric variety on its own and you didn't know any of this setup, you wouldn't really know where to start with proving Morse conjecture. Like these manifolds M certainly do not have to have these properties where if they're elliptic, they're just a product of spheres. And if they're not elliptic, then they have a retracted wedge of spheres, right? These manifolds may not look like that.
So you can handle those toric orbifolds as well.
Yeah, orbifolds, all kinds of like homotopy orbit spaces of ZK.
This is good.
I guess just for the case of like, for example, flag varieties or Bott-Samuelson varieties, I know they're not toric, but like they're kind of being close in some way. I don't know if there's anything that can be said in that case.
That's a good question. I don't think I can realize a flag manifold as one of these quasi-toric manifolds, as they're called. The generalization we'll see in a moment. Bott-Samuelson, I'm not sure. I don't know. Is there anything you can tell me about Bott-Samuelson manifolds that I forget?
I don't know that very much, but I think
But
I was
usually
talking to
not
someone. The thing is, like for Bott-Samuelson, I think they have some smooth degeneration to toric varieties. That's what I heard. I don't know whether that's true or not. And that smooth generation is kind of homotopy invariant. So I don't know if that.
Yeah, Bott manifolds, certainly, or Bott varieties, or generalized Bott manifolds, as they're sometimes called, those will be, well, I guess they're already toric varieties, but
Also, many homogeneous spaces like Grassmannians, steeple manifolds, or Grassmannians, anything that has a torus action, you can often bring to bear some of the tools of toric geometry.
yeah, there's all kinds of other varieties you might ask, but like spherical varieties and things that people studied a lot. Maybe you could get away doing a similar thing, I'm not sure. Seem to only have colored chalk. Okay, so maybe we should just start. That's not white. Okay, this part might also be a little bit fast because I want to give Davis and Januszkiewicz's original definitions before getting to Buchstaber and Panov's reformulations of them as polyhedral products. And then for the rest of the lectures, it's all going to be about the polyhedral product point of view. So I think we can be a little bit quick about this first part. But to start, the combinatorial input for Davis and Januszkiewicz will be simple polytopes. So let P be a convex polytope of dimension n. Then its facets are just the codimension 1 faces. So n will always be the dimension of the polytope, and I'll write m for the number of facets. Okay, let me write something and then I'll put it up there so you can see it. We say a polytope is simple if exactly n facets are meeting at each vertex. And a nice property of these kinds of polytopes is that every like code dimension k face can be uniquely written as an intersection of k facets, generalizing this defining property. So it's like uniquely an intersection of k of these facets. So that's a simple polytope. And sort of dual to that, we say P is simplicial. If every face is a simplex, I guess. So every facet has n vertices. Right, so every facet is like a triangle or a 3 simplex or whatever dimensional simplex it's supposed to be. Okay, example, I guess like any simplex, I'll just draw some 3-dimensional things, but this is both simple and simplicial. Something like 3-dimensional cube, simple but not simplicial. And let's see. That would be simplicial but not simple. And there's a duality here. You can pass back and forth from simple polytopes and simplicial polytopes by essentially, exchanging the role of facets and vertices. So are these two are not dual, but they're almost like the dual of this one would be like this guy, right? So that's simplicial, but not simple. And the dual of this simplicial one is like a prism. Which you can check is, yeah, simple, but not simplicial, right? Because it's got these like square facets. Okay. So that's the only combinatorial input we need for Davis and Januszkiewicz's definitions. So here are the original definitions. Davis, Januszkiewicz. Let Pn simple n polytope with m facets as before. Okay, then first definition, the moment angle manifold associated to P is going to be some smooth, closed M plus N manifold, which they essentially just define like this. So I'll call this ZP. It's just the M torus cross your polytope modulo some equivalence relation where 2 points like point in this torus, comma P is identified another point if and only if okay, so the 2 points in the polytope have to be the same. You're only going to be quotienting stuff out that sit above the same point in your polytope. And whatever this point is, it sits in the like relative interior, the unique face of P. So let me just write something like, if this point is in the relative interior of the unique face, that can be written as like Fi1 intersect Fik, those K facets. Then above this point, T1, T2, inverse will have to lie in the corresponding like coordinate subtorus of T. So S1, I1 cross S1, IK. So that's just.
You need to label the circles in the torus by the facets.
Yeah, so hopefully this is somewhat clear. Sitting inside this M-fold product of circles, we just pick out certain coordinates corresponding to the facets that uniquely determine where your point is. Okay, so that's their construction of some manifold. I don't think much is obvious about this manifold directly from this, aside from its dimension maybe. And that's the main definition, but 2 auxiliary definitions that come with it.
You're going to get a prize. $3,000 prize.
Sorry, is it? I guess I know for special cases I can compute and see this is a manifold, but in general, I guess for simple ones, you have a way to justify this is a manifold, not a random thing, right?
Sorry.
So like when you do this quotient, how do you see it's actually manifold? Because
yeah, why is this a manifold? That's something that I would say is not immediately clear to me. Why? We'll see an example here in a second. I don't know, maybe it's not so hard to see by thinking of like where things are actually being quotiented out. So like on the actual like interior of the polytope, notice nothing's being quotiented anywhere. Then on smaller and smaller facets, right, where you've got like little cusps and things, you're quotienting out bigger and bigger subtori. But yeah, from this quick definition I've given, I don't think things like that, smooth or closed, are immediate at all. And again, these won't be the definitions we'll be working with as we go forward.
Differentiable structure probably needs intersections and quadrics.
That's the only way I know how to put a smooth structure on a moment-angled manifold. Yeah, so there's a.
Not obvious.
If you
Any questions online?
There's probably a lot to say about this, and I shouldn't say too much, but if you take the time to describe your polytope as like, using a bunch of half spaces, write down equations for a bunch of hyperplanes and take intersections of half spaces, then you can use those equations, that data, to cook up like an intersection of quadrics, coaxial quadrics intersected with the unit sphere and you get something which is maybe more obviously smooth that you can identify with this manifold. So that's the only way I know how to get like explicit smooth structures on these things. Okay, yeah. Okay, thanks for the question. Two other quick definitions coming from Davis and Januszkiewicz I should mention is just that, okay, this space has an M torus action, which is the obvious left translation thing here. That turns out to be a smooth action, and the homotopy quotient of Borel construction ETM product over torus P. This is called the Davis-Januszkiewicz space. So the TM action on here is not going to be a free action in general, but you can quotient out by the whole thing in a homotopy theoretic way anyway to get to some space called the Davis-Januszkiewicz space, which they used to compute the cohomology of a bunch of spaces that sit in between here and here as quotients of like actual free torus actions. So one more sort of non-definition is going to be that Januszkiewicz then, this is the whole point of their paper, also associate to our polytope and any, it's called characteristic function, lambda, which will just go from the set of facets to a lattice of rank n. It's just a function defined by some regularity condition that says whenever you have a face of P, describe it as the intersection of some subset of facets, then the images under lambda of that set of facets should span like a K dimensional summand over here, if K is the codimension of your face. So it's more than just some combinatorial information, but to the polytope, any sort of geometric data, they associate a bunch of toric manifolds. We'll draw a quasi-toric manifolds. So they called them toric manifolds, but this clashes with words that algebraic and symplectic geometers use already as toric manifolds. These include those and much more. Okay, so this I won't define so precisely, but it's a very similar construction. So now instead of taking the M torus, you'll just take an N torus, where N is the dimension of our polytope, cross that with your N-dimensional polytope, and you have some equivalence relation on there, which depends on this function lambda.
That lambda, it picks out a subtorus, a subtorus of Tn.
Yeah.
N minus n dimension subtorus.
Yeah.
The equivalence relation depends on.
So in a similar way, you're quotienting out certain subtori sitting over points in your polytope, but you're using this function in the definition. So anyway, in this way, you get a bunch of manifolds that are even dimensional, and notice they come with like a half-dimensional torus action. So these are some smooth 2n manifolds with locally standard torus action. And locally standard just means locally, like in charts, it looks like the standard action of Tn on Cn. And notice that the orbit space of this just obvious, like coordinate-wise multiplication action, orbit space is just like a quadrant, right? Like Rn plus. So that's looking in the quotient like the neighborhood of a corner of a vertex of your variety. So if you quotient out by Tn on this space, you just get your polytope P. Okay, and something you get from a locally standard torus action is that the quotient of such a thing is like a manifold with corners. So that's how you identify the orbit space with the polytope. And in the case of toric varieties, that's your moment polytope or orbit polytope of M. Okay, so a minute ago I said something about these quasi-toric manifolds sitting in between the moment angle manifold and the Stavis-Januszkiewicz space. So just briefly, every quasi-toric manifold that comes about this way over a given polytope P can be described as a quotient of this moment angle manifold by some freely acting subtorus. Right, so this was an m plus n dimensional space. Quotiented by this, you get your even dimensional manifold, 2n. And from a homotopy point of view, this is the upshot here, right? We get a vibration like this. And like for any given simple polytope P, there are maybe many toric manifolds or quasi-toric manifolds over P, but there's just one moment angle manifold, which is this here. Thank you. Yeah. So although there can be lots and lots of quasi-toric manifolds over a polytope, right? This in toric geometry, one tries to classify them, some combinatorial terms. But there's just one of these spaces functorially associated to P, as we'll see. Functoriality is maybe not so clear from the definitions we've seen so far. So from a homotopy point of view, we can just study this one space and its homotopy groups, for example, determine the homotopy groups or control the homotopy groups of just all toric manifolds. Okay, so that's the sort of universal role that moment angle manifolds play in this theory. And now I think we can get a bit more precise and give some more modern definitions. But maybe if it's been an hour, this is a sensible place to break before